Hello and welcome back to these tutorials. This is another tutorial on reverse engineering. We're going to do a full walkthrough of a CrackMe to try and figure out how to get the password that's inside the CrackMe. And this is rated as a difficult level 4. I'm going to put this link on the description for the video so you can follow along if you want to. But yeah, let's have a look. It's a Linux binary and let's have a look at it. First, we'll just see how it runs, and then we're going to open it up in Ghidra and try and reverse it. So this is the CrackMe. I'm just going to run it. And just like many others, it's asking me for a password. I'll try type in password 1. It says wrong password. Okay, so we're going to reverse it and see if we can figure out what it's expecting for that password. So this tutorial is in support of Rob Lawrie, who is a guy from Leeds in the UK who does a lot of work with children in refugee camps around Europe, France and Greece. And so he regularly makes trips down there with a van load of stuff that people have donated, so warm clothing, shoes, to protect their feet. Often they've got their shoes are in very poor condition. If they've got shoes, they've walked many, many miles. So it makes a big difference. And just to be a familiar face for them. So if you enjoyed this tutorial and you feel like doing something, then I'd appreciate if you send some money to this guy here. You can, if you go to his Facebook page, Rob Lawrie, I'll put the details in the video description, and you can just PayPal money to him, or just read and find about more what he's doing, and it might inspire you to help in your own way. But yeah, he's doing some great work. So just thank you very much.
What I do, I'm showing this now. There's lots of children in the camp at the moment, and where's his shoes? Where's the shoes he had? His old shoes.
It's the old one.
This old one. And this guy, most of them are walking around in shoes like this. And with your money, all I do is bring them to my friend Roman. Say hello, Roman.
Hi.
Intersport, and we have a cracking deal on these. So these are work out about €12. And the kids like this go from these. Come on, buddy.
Thank you. It's good?
5.
5. High 5.
Yeah. And that's it. That's the basic principle. You send me money, I buy shoes. And Roman helps me. Say bye-bye, Roman.
See you.
Okay, so let's get this opened up in Ghidra. So I'm going to open up the code browser. And then the first thing I do is I import file, and it's this one here, CM002. So we're going to open that up. Yep. Okay. Do you want to analyze it? Yep, we do. So we analyze it. Okay. Now, the reason why I'd like to run the CrackMes, as most people do, is so that you can see kind of you can find something to latch onto. And in this case, we're going to look in the strings. So if we go on here into Windows and we look for, where are they? Defined strings down here. So if I look through all these strings that have been found in the binary, there are some. Okay, so there's some here. Wrong password. You found a password. Enter password. I'm going to follow this one, enter password, because often it's a nice idea to just follow the input that comes from the user. It's the same if we're looking for a vulnerability, maybe in a network protocol or something like that. We want to find the entry point where the user data comes into it, and then we can follow it through. In other scenarios, you might look for different things. Similarly, like you might look for where a file is read by a system and then parsed, and that gets you to the code that you want to look at. So in this case, it says enter password, so I'm going to click on that. And you'll see it takes me to this area here. So now what I want to do is find cross references to this. Now I'm going to just move these windows around a bit. I'm going to close that. Nice thing in Ghidra is these windows where you can, for example, you can have a split screen like that. Or what I'm going to do this time is just put these on top of each other so we can see more. So this is a string, enter password, and you can see here it's the analysis picked up some cross references to these, and it's got 2, but it's the same address for different reasons. But we just click on one of those and it will show us where this is being used. Okay, so this is my string now. So this is the assembly I'm looking at now. But of course, To get a good idea for what's going on, we're going to look on the decompiled version. Okay, so here's a function, and if we look down here, we can see put s, enter password. So this is the prompt where I'm being asked to enter the password. And then after that, we see fgetS, which is reading. fgetS reads input from the console, so in this case from standard in stream, so the keyboard when the user's using the application, and it reads it in there. So we can see here, this is where our password is coming in. So as before, we want to start kind of refining this output that Ghidra's given us, which is great and it looks pretty good. But let's just start renaming things so we can figure out what the heck's going on. So I know that this fgetS, I know that it reads a string, which is it will be a pointer to characters. So I'm going to just update this type now. Now we can do that in here by, if I go to actually, so something that I noticed on here, if you look at this function, if I go back to here in my assembly view, I see that it's got this is a label for the function, but it's not actually recognized as a function. So for some reason, the analysis didn't pick this up as a function. So what I'm going to do now is, if you see that happen, just go create a function. Boom, there we go. So it's recognized that as a function now, and it's picked out these local stat variables. So the way it works with the stack is that, so local variables are stored in the stack of a function. Stack is just something where you can push things onto it and pop things off it. And the stack gets set up, in this case, with this part here. So it sets up some space on the stack. The stack grows down, so that's why we see sub. So it reduces the stack pointer, and it's got all this space on. So the analyzer knows that it's got this space on the stack, but then when it goes through the code, when it's analyzing the code, it sees the code referencing different points on the stack, and that's how it kind of starts to define the variables on the stack being used. But it's never perfect. We need to try and refine that. So that's what I'm going to do now. So we've got this as a function, which is good. And so what I'm going to do now is, remember fgetS gets our string. So I'm going to go on here, I'm going to rename it, and we're going to call it, just like in the last CrackMe, I'll call it input password. This reminds me that it's come from the user, so I can follow it through. Now, interesting, there's all this other stuff on the stack here, all these other variables, and it looks like they're separate variables, but if I look on here, I can see that input password, it currently recognizes it as just an undefined. Yeah, and so I know this is going to be a character array, so I can do retype variable here, and in here I can say it's a char array, and I can say, if you look here, fgetS, this is the length of bytes that it's reading in. So let's just assume that it's a char array of 100 hexadecimal, which is 256 decimal. So I can change the type here by just doing this. So I set that, boom. That's good. So now you can see that it's recognizing this input password as a character array, a string of 256 characters, and it's reading stuff into there. Now this part here is interesting. If we look in the, so it's initializing that array, so it's all 0. And if we look in the listing, the actual assembly listing, you can see here it's using this function, which we didn't see in the last CrackMe, which this one's running on Linux. The other CrackMe that we did, the last one, was Windows executable. So the compilers will generate slightly different code, or greatly different code, maybe. But anyway, this one, it's decided that when it's initializing this array to 0, it's using this move APS thing. And the reason it's doing this is just because it's an efficient way to put lots of zeros into the array. That's all it's doing. But this is something that when you see something like that, and you're just looking at assembly and you've not seen it before, you might think, well, what's all that doing? Is that part of the CrackMe? I've got to figure out what that's doing. But then when we go back over to here and start working in the decompile view, we see it's just initializing this input password array. So nothing interesting really. And part of that's part of the battle, or most of the battle in reversing stuff, is figuring out what's interesting and what's not interesting. Sometimes you get lost in the stuff that turns out not to really matter in the end. But that's part of the challenge. So we read the password in here, and then what we're doing then? Well, you can see here it's using string len, which calculates the length of the string. So where it says sval1, I'm just going to rename this to len, like that. So now I know that's the length. You can see here now, because I've defined this as a character array and it's saying input password length -1 equals 0. It's just making sure that there's a terminating 0 on the end of the string that's been read in for fgetS. If you look on the man page for fgetS, I forget these things. If you look them up, you can find out for sure. But I think that it might be the case that if it's reading 256 characters and somebody types a password of 256 characters, it means that it will get copied into the buffer without the terminating 0. So that's why often code adds a 0 onto the end of the string to make sure it terminates. Otherwise, it could lead to a vulnerability. So anyway, that's what that's doing. And then what we've got here, let's see what's going on here. So we've got an if statement here. If 7, that's a greater than length. So if the length is greater than 7, it's going to do stuff down here. And then it's got some other stuff down here. So what's going on here? First of all, we can see it's taking the input password and it's storing that in here. So let's call that pointer to password. Doesn't matter what you call it as long as it helps you differentiate some of these variables because they all look quite similar. So it's got the password, so we get the pointer to the password, and you can see here that it's copying the character. So it's looping through the password and it's copying bytes from the password and storing them somewhere else, and it's storing them here. Now, this points to this looks like some kind of global variable, so it's pointing to some other data area. So in these binaries, if you look on here, there's a view at the top that shows you, it says program trees, and it just shows you the structure of the binary. So the binary, different binary formats, Windows and Linux, but they're quite similar how they work. They have different sections. And so you've got the main one. So if you look at, text, as it's sometimes confusingly known, means the code. So that's where all the code gets compiled to and put into the code section. But then you've got other things like data, which is where things like global data go. In fact, if we look on, if you look in window on here, there's a thing called memory map, which is quite interesting to look at how this stuff works. So this shows you all the sections in the binary. I'm not going to talk about all of these, but you can have a look. It's a good way to learn. They've gone. So this shows you all of the sections in the binary, and you can see, so the text one here, you can see that some of them have these flags on to say whether, when they're loaded into memory, when the process starts, whether they should be read-only areas of memory, they should be writable, and if they can execute code in them, which are used for, this is used for kind of to mitigate certain vulnerabilities, stuff like that. So the idea is that only the stuff that can execute as code is stuff that was compiled as code in the binary, not stuff in random memory. And so we can see these in here. So it's interesting to look in here, and it shows you where they load into memory, shows you how long they are. So so this is pointing to what I like to do. If you click on, see this little window up here, these have got little toggles on here, and this little toggle, shut my curtains. This little toggle here, it says toggle on means to select the fragments that correspond to the current location. I find this quite useful when the code seems to be hopping around in different sections. So if I click on this, like this, then now I'm looking, because I'm in a function here, I can see this function is defined in the text area. But if I click on something like this, if I go to my listing, because it's not code, this is data. You see it's got some values in it. We can see lots of references to this data, and it's showing me now, because I clicked on this thing here, it's showing me that I'm looking at stuff inside the data section of the binary, which is interesting. We'll find out in a minute why. So it's referencing a global variable there. So I'm going to call this, I don't know, I'll call it password dest or something like that. I'll just call it dest, because it seems to be copying something to that. So we can see now, looking at its code, that it's taking bytes from password and it's copying them to dest. Now, this loop here, at first when you look at this code, you might think, oh, this looks interesting. It could be decoding something or something like that. But I'm going to split my windows off again now, because when you look at what Ghidra's done here, can we do this? Yeah, good. Now, see all this loop here, this for loop. When you click on code in the decompiled view, it takes you to the line that corresponds to it in the assembly view on here. And it's always good, although the decompiler is really good and it really helps you find stuff, it's always good to reference between the decompiler and the assembly view, because sometimes the assembly view actually shows stuff more clearly than the decompiler, and especially for lower level stuff. Higher level stuff like the control structure of the function, it's, you know, the decompiler is awesome. But let's have a look, because when I click on this loop, look what's happening on here, all these different lines. They all relate to this single assembly function, move sq rep. And this function is, it's like a multi-byte, it's like a looped, low-level loop assembly function where you can pass it a start address in RSI, and you can pass it an end address in RDI registers, and then you give it a length, put it in ECX, and then you just say call this function, and it copies all those bytes. So this is a good indicator that we're actually, what we're really looking at here is just memcopy. It's just copying the password to a location in memory. And in fact, if I show you I won't go through this whole function. I might do that in another presentation, another tutorial. But if we look at this function now, okay, so all I've done here is just found the source code for libc for the memcopy function. Now, this might not be the exact implementation that was compiled into this thing, but you can see how it works here. So memcopy, the whole idea of memcopy is for copying loads of data from one place to another place in memory. So it makes sense that it's done efficiently, as efficiently as possible, especially if it's used lots and lots. And also, we didn't see a call to a function for memcopy. We just saw the thing plonked into the function here, which is, because it's been inlined, it means the function has been inlined into the code. So there's no function call. It's just inlined into that function to make it more efficient. Because when you call a function, you push stuff on the stack usually, and you call the function, then you return. So it's just saves some overhead. Now, if you look, it looks quite similar to what we've got here. So there's an if statement here saying if length is greater than some threshold, and we've got here if length is greater than 7, then it does this stuff, and then it does this stuff at the bottom. And you can see here, down here, it says if the length is greater than, let's say that's the same, so 7. So if it's 8 bytes or more, then it does this stuff, which basically tries to copy. It tries to optimize it so it can copy like 8 bytes at a go, as quickly as possible using some assembly instruction, some CPU instruction. And then when it's done those like multiples of 8 bytes, then it goes on here, it drops through the bottom, and then it copies individual bytes for the remainder of the thing. So it copies the bulk of the data as fast as possible, then it just copies individual bytes. And that's what we've got here actually. I'm not going to go through this in too much detail, but you can see here it's copying this stuff, and it's actually here. You can see it's this is called undefined 8, and that function that I clicked on, so that means 8 bytes, an 8-byte type. This thing here, it says move sq, and that means quad word, means 4 times a word. A word is 2 bytes, so 4 times 2 bytes is 8. So it moves 8 bytes at a time to the destination. That's how it works. Which is also why they take the length of the string here and they shift it right by 3. You can see Ghidra, Ghidra's done the shift 3. Just got to close his curtain. It's shining on me. Yeah, so it shifted it by 3, and when you shift right by 3, a shift by 1 bit is a divide by 2. If you think about the binary data, so shift by 3 is divide by 2, divide by 2, divide by 2, which means divide by 8. So it's taking the length of the string, dividing it by 8, and then it's copying that many chunks of 8 bytes across. Anyway, I'm not going to spend too much longer on that, but this is doing a memcopy. So our password is getting copied into here. So we're going to rename this data here as input password. Buffer. What am I doing here? Input password buffer. Something like that. It doesn't matter what you call it, as long as you know what it's doing. And it's quite common when you've found something to rename it later, when it becomes clearer what it's doing. But it's better than just having a random number to look at. So it's copying the password into here, and then so this is all part of memcopy here, and then it calls this function, and it passes these things in, which again look like global addresses. I don't know what these are. I don't know what they are. These are in the text area, so they could be functions or data. And then there's this thing here, so I just clicked on here. Now, when I click on there, something to notice is that it's calling this function, but there's no function found here. So if I do function, well, yeah, it's not. Let's try doing that. Nah. So we've got cross references to this thing, and it's calling it like a function. Now, the other interesting part is that it's, if you remember, I synchronized this program binary structure thing to show me which, so I click that button, so it shows me which area I'm in of the binary. And yeah, so you can see that when I go to this function, so I'm in the text area now, but when I click on this function, I end up in the data area. Now remember, it's calling a function in the data area, but remember from here, from my memory map that we looked at before, if we look at the data area here, it doesn't have execute permission, so it shouldn't be able to execute. So there's something interesting going on here. And also that function is garbage, so it looks like it's been encrypted somehow. So how does this work then? Let's go back again. So what we need to do, well, yeah, what we need to do now is look carefully at this. So this, if we look at this function here, which looks like it's our main function. In fact, if we click on, yeah, there's the entry cross-reference. So if I click on here, yeah, so this is all applications, all these applications start with the entry function. And then they call libc main, libc start main. And I know that the first argument to that function, if you look it up, is main. So I'm going to rename that main. So this main is my function I was just looking at. So this is where it's collecting the password and stuff. So let's go back from there. So what are these other things? Because what we're looking for now is whenever you have something like a packed binary, which is where it's been obfuscated, encrypted somehow, what's going to happen is when it runs, it's going to decrypt that stuff. And the reason it does that is not to stop it running. When it runs, it's going to decrypt it and run as normal. But it just means that when you're reversing it statically like we are, so we're looking at the binary to try and figure out what it does, that we can't make sense of it until we've decrypted it. So it looks like that's what's going on here. And the way that works is, I'll just talk through this libc start main function. But this is what kicks off our application. It runs some initialization stuff, and then it runs our main function. So when we write our main C function with like hello world or something, although it looks like it's our entry point to the system, when the process loads the entry point, this entry point is the first point, the first code that gets run in the application, and it does this other stuff. Now it turns out if we look at libc main, the documentation, let me just see if I can find it. Right, so this is libc main, I just googled it. This is the function. So it takes the main method, which we already know, and that's the format of it. It takes argc and argv arguments. And then if you look later on, it's got this, it takes another function, init. It also takes a fini and some other stuff. But the ones that are interesting, well, the one that's interesting to us is init, because it allows some code to run before main starts. And usually the unpacker, this is where it's going to do its unpacking. So this is where I'm going to look. So let's go back. So we know now that this thing is actually init, or ini. Let's call it ini, or whatever. Not init, whatever. It doesn't matter. Call it init. So now if we go on this init function, what do we see? Well, it does this stuff. So it runs this code. And this is just boilerplate code that the compiler would have generated, the linker, whatever, when it put it together. And it does this thing. It loops through. It does some initialization. Then it loops through this thing called DT init array. And if I look at this thing, this is actually a part of the binary. You can see now which section I'm in. There's a special section called init array in the binary here, and you can see in here that it's got these things that Ghidra has picked out because it knows these are entry points for initialization. So it's got init 0, init 1, and init 2, and these things are addresses to functions to call before main starts, so initialization functions. And they're used for things like if you're using C++, and you might create a global object in C++ or something that is initialized before your main function runs. So these kind of things are used. So things like this initialization stuff is used to register a function that runs before init. So let's have a look at these things. We can see that actually all these would have been picked up by Ghidra. So all it does in this code, this boilerplate initialization code, is it loops through, it gets this array from the ELF binary, from the binary here, and it loops through these pointers inside these positions, init 0, init 1, init 2, and it calls them as functions. So if we look down here, Ghidra's functions, we'll see that it's got these. So init 0, there we go. So this is init 0. And we can see there that calls a function which does some stuff here. So this is a function. In Ghidra, it's just got this as return. And in fact, this is just, so it's doing something with standard in. This is some kind of initialization of the standard input, and it's just boilerplate stuff. If you look in other binaries, you'll see the same code in those. So it seems to do some processing based on whether standard in is 0 or not, and then it seems to call a function. But we won't worry about that because it's just boilerplate. Init 1, what does this do? Okay, this looks interesting. So this is doing some stuff. So all these functions run before our main function starts, which is why we're looking, because we want to figure out how it decodes that function that's all mangled when we look at it statically. So what does this do? Well, it calls a function, it does some stuff to it. Let's have a look at inside this function. What's this doing? It's just a short little function. Okay, this instruction here is a timestamp. This is for getting a timestamp from the CPU. Let me just see if I can get a reference to that. Okay, so this is just, I just googled that instruction, and so it says read timestamp counter, so it loads the current value of the processor's timestamp counter into these registers. So it's getting the timestamp of the CPU for some reason. So let's see if that's of any interest in this CrackMe, or it could be some boilerplate stuff. It could relate to another piece of code that is being used by this thing. So read the timestamp. Let's just call that timestamp CPU timestamp. And so we can see it's doing some masking and shifting of bits and stuff. It's doing some manipulation to the timestamp, which could be just like bringing it into some standard representation or something like that. So let's go back out of this function now. So it returns, it looks like timestamp, CPU timestamp. Yeah, it looks like it's returning that timestamp with after some manipulation of it. So let's go back here. Go back out of that function. So we'll rename this function read timestamp. Okay, and then we'll go back out. There's there. Okay, so read the timestamp. We'll call that timestamp. Okay, so it reads that. It does some more stuff to it. If you look in the assembly for that, where is it? Read timestamp, doing this stuff. This looks like it's an optimized division. I'm going to look at that more in another tutorial to explain how compilers do stuff. It looks like it's dividing it by a constant number. But anyway, it's just processing that timestamp, and then it seems to be using this value. So what's in here? 0, it seems. So that part in the data. And then it seems to be storing the result of that in here. So I'm going to rename that to timestamp as well. And what we really want to know then is if it's, so it seems to have grabbed the timestamp from the CPU and it's stored it in here. And what we want to know is, where is this used? Is it important for this CrackMe? But you can see in, if you look at the cross-reference here, that it's picked up on this, we can see that the only place it's referenced, it seems to be here. So it's basically, it's got the timestamp and stored it globally. So it could be used later for something, for some reason. It could be something the developer did, or it could be some boilerplate thing that was done. But I don't think it seems to be used. And if it is, we can revisit it later. Which leads on to this one, which does look interesting. So yeah, so now the clue on this CrackMe was something like think outside the box. So to me, that made me think maybe they meant think outside of the main function. So something like it was packed or something like that, which it looks like it might be the case if we look at this. So this final init function that runs before main runs, it's using mprotect, which changes the protection permissions of memory in a program at runtime, and it's doing some stuff. Now remember, we renamed this to input password buffer, and you can see it's referencing that data where the password was getting copied to, which is interesting. But what's interesting here, well, you'll see this used over and over again, but mprotect here, that 7 on the end is actually I wonder if it will show us in Ghidra. Yeah, it does do. So down there it says the final argument is prot, which means the protection bits. And if we look these up on the web, let me just see if I can find them quickly. Just one sec. Okay, so I just did a search for the source code for the function, and you can see down here that these things are defined. So these are the protection bits, how they're defined. So protection read, protection write, protection exec. Now 7 was set, which is the same as 4 add 2 add 1. So all the bits were set for read, write, execute. So what's happened is here, when this runs, the data area, well, the region of memory that starts at this password buffer, which, remember, if I click on it, is in the data section of the code, which, if we remember from the memory map, tells us that the data area is not executable by default, so it won't have been executable, but then they've called mprotect, and they've changed it to become executable. And this is the number of bytes they've made executable. So it looks like what we've got here is that memory region. So for 100, so 13C, so it should go from input memory buffer 41000 is where it starts. So it starts changing protection all the way down to 13C, which is, well, it's show me 13C is in decimal, that's 316 bytes. So it's going to get 316 bytes from here. So if we go all the way down here, it's going to become executable all the way down here. So we're looking for 13C all the way down here. Okay, so it's into that function that we suspected has been encrypted all the way down here. There's 13B. So it's going to do all this is going to be decrypted, which is what we were kind of suspected when we looked at this function. So it's going to get decrypted. So when this runs, that's going to get decrypted, and it should become executable code, that function. So how does it work? Well, we can see here that it's getting the password. It's storing that in there. In fact, no, this is not. So this is not just the password. This is also what we suspect is our verify function. That checks the password. So they've obviously encrypted it so that we can't just reverse it and say, oh, how does the password check work? So let's rename that to password buffer and verify function. I'll call it func. So now I know that that's what that's used for. So it's going to go through there and do this stuff. So what's it doing? Well, it looks like it's taking, so let's call that pointer to memory. So p mem, so it's getting the pointer to memory. It's got this constant value here, which is then XORing it with. So this is kind of like the key. And like in the last CrackMe that we looked at, it's not, if we look at the code, it's not just a static key that we just take that key and apply it to all the bytes, but it's a key that changes through the loop, which is just a way of making it slightly harder. So we need to execute the loop to keep, so I call it a key stream. Oh, it's probably a better name for it, but I know what it means. So it's the key stream, it's the key, and we can see there that algorithm does that. So what we need to do now is run this to decrypt the memory, and then we can start reversing the CrackMe function. Now, there are at least 3 ways to do this. In the last CrackMe, what we did was we looked at the verification function, and we created our own, we reversed it so that we could create our own implementation of it in Python, and we ran that to brute force a key. The other thing we can do is we can run this in the debugger. So Ghidra has a debugger, or you could run it in any other debugger. And we can run it to the point that before this returns, or just after it returns, and then put a breakpoint and stop, and then it would have decrypted the memory and we can look at it. So that's okay. But just for now, I'd like to focus on static analysis. And the other way we can do this is using Ghidra's emulator. So we can emulate this code without any risk. So if you suppose, well, this could be a dangerous file that we don't want to really run just at this stage in a debugger. Or it could be, yeah, we could imagine that this is, I mean, we could recreate this in Python, but just supposing that it was much more complex than it appears here, then we can use the emulator or a debugger. But also the nice thing about this function is it doesn't take any input into the function, and the only thing it does is it seems to just affect that memory, to decompile that, to deobfuscate that memory. So it's a prime candidate for just emulating that individual function, and it's a good excuse to learn how the emulator works. So that's what we're going to do next. We're going to write a Ghidra script that decrypts this memory so that we can continue to reverse it statically. Right, before we start Ghidra scripting your first script, it's worth getting a cup of tea. Yep, get yourself a nice cup of tea, and then we can get into it. So yeah, Ghidra scripts. So most reversing tools most reversing tools have a way to script with them, and Ghidra is no different. So if we go down here, we can see there's a thing called Script Manager. So if I open that, let's make it full screen. Yeah, so Ghidra seems to be built around the idea of scripting, so that's quite a fundamental thing to how Ghidra works. Lots of things run as kind of isolated scripts that hook into other stuff. And the best way to learn about scripting, because there is this documentation of the API, but a lot of things you learn just by digging through the API and reading the API, which I'll show you in a minute, and just looking at these other examples of scripts. There are loads in here. Yeah, lots and lots of scripts, all different things. That some of them do some extra analysis on the file, like renaming variables automatically, recognizing certain patterns. Some do some kind of decryption stuff. Let's see if we can find, there's an XOR, one called XOR, I think, XOR memory script. I always run it by mistake, but if you right click on it, you can edit it. So I'll just edit it with basic editor. So this is the source. So we can just look through the source of these. You can write scripts in Python or in Java, and the Python just runs on top of Java using Jython. So it's accessing the same API basically. It just kind of converts it to and from Java to Python types. So this one is doing some XOR, which is interesting to us because usually when you're writing a script, you want to find another existing script that does some of the things that you're kind of wanting to do, but maybe not quite everything you want to do, but it gives you an idea about how to do it. And so this is one that says it so XORs the memory of the current program. So in our case, this won't do, but in some cases you might just have a bit of code that's been XORed by a single byte or a word or something like that. And all you need to do to decrypt it is to run XOR through that range of memory with that value, and it would decrypt the memory. So that's what this is doing here. But it's interesting because we can see things like how it's using the API. So in the API, there's a few global variables. There's one called current program, and this references the program that you've got loaded in Ghidra. And so in this case, if you want to get the memory object of the current program, you just call get memory. And everything in the API is pretty much objects. So everything, memory is an object, sections of memory are objects, instructions are objects, listings of code, function, symbols, everything. The decompiler is an object. So you can get hold of all these objects and inspect them and get other interesting things from them and run functions on them. So that's how it works. Addresses are objects, and so this is what it's doing. It's looping through memory. We're not going to look too much at that one. I'm going to close it now. And yeah, so what we want to do is, first of all, just before we start, I'll just close that down. And if we look in help, so Ghidra, all the help can be accessed on here. So just click on here and it will open up the API docs. So the documentation is just generated from the code. So this has everything that you can do with the API, Ghidra API. And so the top level access to the API is called current program. So if I type current program in here to search for that, you can see the variable is there, and so that tells me that it gets a program object which represent the program. So if I look through here, I can see all the things that I can do from the program, like these ones, like get address map, and so all the stuff that I saw in the GUI before, the address map, where I could see that the data wasn't executable but the text area was executable, all that stuff you can just grab it as an object from the API and process that in your own scripts to do stuff. Get listings of code, get memory, we saw that one being used before. So any of these, get registers for architectures where the memory has registers in and stuff like that. There's all kinds of stuff we can do on there, and yeah, so we can drill through this, which we will do when we're writing our script. So let's go back to here. So we're going to create a script now to try and run the emulation to deobfuscate, to decrypt this area of memory that is doing the validation of our password so that we can reverse that code. So we're going to go into Windows. We're going to go into the script manager area. So I've got a filter down there which is useful for finding stuff. To create a new script, you click on this one, and it says, do you want to create a Python script or a JavaScript? I'm going to create a Python script, and then it says what you want to call it, and then it shows you where it is. So that's how you create a new one. I created one ready for this demo, which should be called, named after the CrackMe, this one. So I'm going to open this one up. I don't use Eclipse, so I'm going to open it in there, and it's empty. So I'll just show you how it works. And all I can do, so I can type Python code into here. So I'll just say my script. And then all I need to do, if I save that, then when I click on that, you're going to want to see what this is doing. So if I just reduce this down a bit, you'll see that in my main window, there's a console here. See this console. And when I run my script by double clicking on it, you'll see it prints my script. So this is running my script. That's good. It doesn't do much interesting yet, but it does that. Now, one thing I like to do, especially because I don't like to edit the script in here or Eclipse, I like to edit mine in my own editor. I use Vim, but you can use whatever editor you like. So what I like to do to make this easier is, you can see I bound a key here. If you, there might be another way to do this, I don't know, but this is how I did it. So if you go click on your script, right click on it and say bind a key, and then just do your key. So I do Control R for run. Then it means that if I go back to my console thing here, I'm going to put the console at the bottom down there, if I can stick it down there somewhere. I'm going to put this back on there, and then the console down there. Just move your windows around, that's better. There we go. So now if I just do Control R, it runs my script, which is good. So it means I can build my script up. So I'm going to go up to my editor now with my script, which is, so this is my script. So what I'm going to do, first of all, I'm just going to put some comments in it. Okay, I'm just going to give it a bit of structure now. So it's just normal Python. So if name equals, I like to do this because it just means that if I want to, I can import this as a module. In fact, before I do that, let me just show you something else. So if I go back to here, there's another window up here called Python. And if you click on Python, it gives you an interpreter, a Python interpreter, that you can just interact directly with the API on. So it's useful when you're scripting. If you're starting to write a script, rather than running the script over and over again to figure stuff out, you can just write little bits in here and see what they do. So we remember that current program is a global variable, program, current program. And then nice thing is it's got things like autocomplete on here. So I should be able to do like get memory, which is what we saw that other plugin using, and you can autocomplete, get memory. What's that going to do? I got an error. I must have missed. Okay. Well, that didn't work. But you can basically look around the API like this, and you can also, if you want to get access to help on it, this should work. So if you type the Python help function, it dumps out the help that we've also got in the documentation. So this is help from the Java docs, but it gets converted to Python when we're using it. So that's quite useful for just trying stuff out. So I'm going to close that for now. Then we're going to go and write our code. So what we're going to do on here, so we're going to build up our script, and I'll just get rid of this now. So I like to do things in objects. So I'm going to call this object memory decoder. The reason I do this is because then you can break it down into different functions, and they can share a bit of state inside the object, and you can reuse those bits in other, when you come to write other scripts that might be similar to this one, you can just reuse that stuff. So I'm going to do that now. I'm just going to start to fill this out with stuff now. Okay, so just some things here. So the decode function, remember, if I go back to my stuff here, is called init2. So I'm just going to store that in a variable, in a constant. Decode memory start, the address that we start decoding memory from is this thing here, which if I click on it, it's this address. So I've just put that in there. And where do we stop decoding? It's here. Okay. And then what I'm going to do is I've just got an init there. I'm going to store the emulator in a variable, so I'll just set that to none initially. I'm going to have a function called run, which is where I run all the stuff. And that just means that when I run this thing, I'm going to create my memory decoder object, and then I'm going to call run on it, and it should run this here. So we've just put a print statement here saying print running memory decoder. Okay, let's get rid of that. And let's just run that just to check that I've not made any mistakes, which I probably have. But so if I do Control Shift and R because I've bound that key, and you can see it's saying running memory decoder. Good. So I've not put any syntax errors in there yet, but I probably will do shortly. So that's good. Right. So there's a few phases that we're going to go through, and I'll build them all up. But we've got first of all, we want to set up the emulator. So I'll call that setup emulator. Just leave that for now, and then we want run emulator, and then we want to tear down the emulator. Because we want to free up any resources that we use when we run the script. We might have to run the script over and over again. So that's good. So in run, what we want to do, just to build up this structure, we want to do self.setupEmulator, and then we want to do self.runEmulator, run emulation, self.teardown. And because we want the emulator to get toned down in any case, whether we fail or whatever, we'll just put it in a try finally, if I can spell it. Try finally. Good. Right, I'm not going to just type these up one character at a time. So first of all, we're going to identify the function to be emulated. We stored that in here, so decode function. And I've put a call here to get symbol address, which is something I'm going to define in shortly to show you how to get the address of a symbol, so like a name, a label or something, from the API. So that's what we're going to do. And then we're going to create the emulator. So there's a thing called emulator helper, which we just need to import. So that's this thing, emulator helper. So we create that. The emulator helper is it's the Ghidra wrapper API around the actual core emulator, and it just makes it easier to set registers. And we'll see when we're working on the code. But the emulator tries to. So Ghidra will take loads of different CPU kind of instruction sets, ARM, x86, whatever it takes, or some other processor, and it takes those and it turns them into an abstract instruction set. They call it P code or pseudocode or whatever it means, but that represents what that instruction does to all the registers explicitly. And so it changes whatever CPU is being passed from the binary file. It abstracts that into this sort of universal P code stuff, and it's that you could use with the emulator. You can interact with the emulator and you can say, like, I want to get the instruction pointer, and the instruction pointer will be a register. It might be the RIP register on the stuff we're looking at, but on a different processor it might have a different register. So it abstracts stuff like that, so you don't have to. You can write a script that works with different. It does analysis on different instruction sets and things like that. So the emulator helper does all that stuff. But again, we can look in the API for emulator helper to find out more about how it works, which we'll do as we build this up. All right, so some of the things we need to do. When we've created the emulator, the first thing we probably want to do is to set up the registers for our emulation, and we need to give it a stack, which I'll create this function. So I've called it setup emulator stack. I'll define that in a moment. And then we need to set the execution address of the emulator to start at the function we're emulating. So it's going to, when we start the emulation, it's going to start at the first instruction in that function, which is this one here. Okay, that's good. Okay, so I'm going to start defining these util functions. So I usually do it like this. So there's these functions, so get symbol address. Now, the way we do this in the API is there's in fact, we need to import this. So we'll just import that. Symbols utilities. You'll see these used in lots of those example scripts. So look through the scripts and you'll see them being used. But what we're doing now, so we want to get the symbol address. So we pass it a symbol, like the name of a function that's got a label that we've labeled or something, like init. In this case, it's init2 is the function name here. And we use the symbol utilities to call a function, get label or function symbol. We pass it the current program, because that's the context of the thing we're looking at. Because you could open multiple programs. Your script could open multiple programs and do stuff on those. So we don't just assume that it's which program we're analyzing. So you pass that into there, and then the symbol name. And if we don't get symbol back, we'll just raise an exception to say we failed to do it. And if we do get a symbol, then the symbol is an object. So if we look at let's just have a look at this in the API, symbol utilities. Or in fact, we'll look for get label or function symbol. Okay, so this is the API function that I just reference there, and you can see it returns a symbol object. Like I said, everything is represented as an object, so a symbol, which is useful because if it just gave us a string saying the value or an integer saying the address or something like that, we wouldn't be able to find out any other information about that thing. So this, if we click on symbol now, it shows us all the information about a symbol. You know, get address. It can also tell us how many of them there are. Where if it's got references to it. So just you can just look through the API like this. So just go in here and look up any of the functions that I use to get more details on them. Okay. Right, so this is what we do. We basically call this API to look up that symbol address, and then we store it in here. So the function address, so the function we want to emulate. The next thing we do is we create the emulator helper. It's pretty standard. And then we set up the emulator stack. So I'll just define this function now. Okay. Here's one I did earlier. So set up the emulator stack. So we pass the emulator in, and we pass in the address space of the program. So which we get from the function that we're emulating. So we can any address, we can get the address space, which just means the program's address space. In our case, it's just the full address space of the whole program. The reason we get that is then we can call this thing on. So the address space is an object. We can look that up in the API, and it has a function called getMaxAddress, which gets the maximum address in the address space. And then we can get, when we get the address is an object. If we look at an address in the documentation, so if we go in here, type address. So this is an address, click on there, address. So an address object has lots of interesting stuff, but the one that we'll use quite a lot is getOffset, which gets us the actual integer representation of that address, which is mostly what we want when we're using the address somewhere in our script. So remember, an address, whenever you get an address from the API, it's an object address. It's got other stuff on it, and if you just want the offset to find the actual number representing that address, then call getOffset like this. So that's what we do here. We get our stack, and this code here is just an example copied from one of the scripts and how they set the stack up. And it just, all it does is it creates a stack. So the stack grows downwards, and so all it does is it gets the top of memory, the maximum address in memory, where nothing will be used, and then it goes a little bit down from there, and it gets a memory aligned address. So it aligns it on like on some sort of 0 on some boundary, some frame boundary or something, to make sure that when we're running code from there or storing stuff from there, it's byte aligned, which is important for the CPU when it's running, especially like multi-byte operations. Anyway, it just creates a stack like that at a high address space. If we set the stack, and you can do this, you can play around with it, if you set the stack to the same addresses like the function or your instructions, you'll see that when the emulator is using the stack, it'll start clobbering the code, and you'll get errors in your code. So it's a good thing to do to see why you need to set the stack up. But anyway, we set the stack up. It could be anything as long as it's out of the way of the code, so that as we push stuff on the stack in the emulation, they don't interfere with the code. And then all we need to do is write that stack address that we just calculated to the stack registers, so RSP and RBP, so the bottom and the top of the stack now point to that stack address, so it will grow down through memory from there, and it's away from all the other stuff. That's what we do there. So like I said, you can just copy and paste these instructions for any other stuff, any other scripts. And the next thing we want to do is set an initial instruction pointer where we start emulation. So let's just define a function for that. Okay, so set execution address. And the way this works is we pass it an address. Remember, an address we're passing around here is an address object. We pass it the emulator. And all we do is we say emulator, and if we look for emulator helper, this thing. So I'll just put that in the API so we can see. Emulator helper. If we click on that, this is our emulator helper, and you can see it's got, these are all the functions. In fact, these are the summary. So these are all the functions, and you can see there's things like for reading memory from the emulator, so the emulated memory. You can set breakpoints to make it stop. It's like a debugger. And you can write registers, which is what I'm using here. Okay, so that's all I'm doing. So emulator.write emulator.getPC register, which means the instruction pointer, the program counter register. Like I said before, it abstracts it from other architectures. In this case, this would just be RIP register, so I could have put that in there. But I'm just using this abstract get PC register. And then I'm going to write the address that was passed into, which is the function address. So set execution address. I pass it the function address that I loaded, which was this function here, so this address. And so it writes the value, the offset, as in the actual integer representing that address, into the RIP register in the emulation context. So it's ready to start emulating from that address. So now we've set up the emulator. Let's just run that and see if we've made any errors in our code, which is quite likely we have. Somehow we've managed not to, which is good. So, right, before I get ahead of myself, I'm just going to define this teardown function so that we can clean up stuff. Let's get rid of that one, little stub. And in the teardown function, all we do is we say if the emulator's been set, then we just call emulator.dispose, which just frees up any state. So it must be like all the the memory that it's got allocated for it and stuff like that. So now we've got set up emulator, run emulation, and tear down emulation. So let's look at the run emulation part now, which is the main interesting part. Right. So the way the emulation is going to work is, as we'll see, is that we're going to get the emulator to step through the instructions and basically run the code until it finishes that function. So one thing we need to do with the emulation is to set when it's going to finish. And the way we can do that is to have a return address so that when the function finishes, return will be called on the function. And when you call return on the function, it basically pops the address of the calling function off the stack and we'll start executing that instruction. And there is no calling function because we're running this function directly. So this is a way, if you look in lots of the scripts, they use the same technique. So what we're going to do is we're going to get a 0 address and push that onto the stack as though we were called by a function at address 0. And then when this code returns, it will pop 0 off the stack and start trying to execute at 0. And that's when we're going to exit this function. So we know that's whenever the function returns, that's going to happen, and we're going to stop the emulation. So we'll call it controlled return address and as address. So this is another helper function I created because remember that addresses in the API are address objects, and if I want to represent the 0 address as an address object, then I just need to map it. So I'll define that now. So down here, I'm going to create function as address. An as address, or I could call it as address object maybe to be clearer, but all I'm going to do is pass it an address, which is a number, an integer, and it's going to basically use the API to get that represented as an address object. So it's going to go current program, get address factory, get default address space, get address offset 0, and that should give me an address object now of 0, which is going to be useful when we want to check for that address. The other thing we need to do though is to push, remember we set up the stack for our emulator, to simulate as though that function, as though we called the function from the address 0, we need to push the address, this 0 address onto the stack, the emulator stack, because it's that's going to be popped off to do the return at the end. So we'll do that now. Okay, so to write that onto the stack, the emulator stack, we can use this. So self emulator, because that's our emulator helper, write stack value 0. I'll explain that in a minute. We're writing 8 bytes. So we're writing the address as 8 bytes. So the address is 8 bytes long. It's a 64-bit address. So we're writing 8 bytes onto the stack. So we're pushing an 8-byte data type onto the stack and address. And that means it can return there. So just to look at, if we go in the API of this write stack value, so this is on the emulation helper. So if we go into the API docs, write stack value, relative offset. That just means an offset from the stack. We just keep that as 0 because we just want it to write to the current stack pointer RSP. And then the size 8 bytes because it's an address which is 8 bytes long. And then the value, which is the actual value to write as 8 bytes, which is the offset of the address, which really I could have just put 0 in here, but I'm just trying to do it, make it clear. So now we've got the return address as 0 on the stack, which is good. So now we can control when our emulation stops, when that function returns. There's also other ways we could do that. We could use breakpoints and things inside the emulator. Right, let's do the actual emulation now. So we'll start our loop. So we'll see this used a lot in the scripts. So there's another global variable that's available to our scripts called monitor, and is cancelled. And this is just a way that scripts can, if you're running a long-running process or you're doing an emulation, you want the user to be able to cancel that process at any time. So we often reference the monitor, which just means it's just like it just allows the user, if they click cancel script, when I'm running this loop in my script, it will see that it's been cancelled and it will break out of this loop and stop. So it's just a way for the user to be able to control the flow of our scripts. So we'll do that. Okay, so the other thing we want to do just before we do this is we want to know if the execution succeeded or not. Because there's a few reasons we might break out of the loop, and that might be because there's an error in the emulation or something like that. So we're just gonna, we want to know if we succeeded running the emulation, then we can do whatever else we need to do after we've emulated that decoding of the bytes. So the first thing we're going to do is when we're running our emulation, this is our emulation loop. We're going to do self-emulator, get the execution address, so the current address that's being emulated, and we're going to check if that equals the controlled return address, which is the 0 address. Then we're going to say execution succeeded, and we're going to break out of this loop. This is how we know when we've finished emulating that function. Okay, I'm just going to add some diagnostic stuff now, so that we can see the emulator as it's running, see what it's doing. So I'm going to create this. We're going to print out the registers for each stage of emulation, but I'm going to do that. Usually I like to be able to configure, if we want to log stuff verbosely, I'll put true. And what we're going to do now, for each time around the loop, we can do this. So all this is doing is saying if we switch our verbose flag on so that we're printing loads of stuff, we're going to take these registers, this list of registers, so RIP, so the instruction register, RAX and RDX, and we're going to print them out. Why these registers? It's because if we look at the assembly code for this function, we can see that the actual, I'll put it on the, let's look at the graph view. So we can see that when it's doing the actual decoding, it's storing the key in ECX, it's storing the key in EAX, and then it's using RDX to point to the memory as it's going through the memory and updating it. So we'll hopefully see those values changing in our emulator, just to give us an idea if we're doing it properly. Okay. Right, so there's something else that's a bit of a problem in our emulation, and that's, although I said this is self-contained, if we look at the code, let's get back to the disassembly. Close that graph. Where are you? There we are. To the decompiled version, sorry. This is called to mprotect. Now, we don't care about mprotect in our emulator because we're just executing. We're just running this function, and we're not bothered about the state of memory because our emulation doesn't care about anything like that. We're just executing the algorithm. So what we're going to do is when we see a call to this mprotect, we're just going to skip past it. We're going to ignore this call. We're not going to try and emulate it. Certain functions, if we are emulating them, we might want to emulate certain things happening, like maybe reading input from the network or something like that. We could emulate that call to a certain function to return a value that we want to control, to flex the code. But in this case, we don't want to execute this, so we're going to skip over this function if we hit it. Okay, so let's have a look. So the way we can do that is like this. So what I do here is I'm going to create another util to get the instruction at the execution address. And I'm just going to do this simple way here. There's other ways you can do it by looking at the P code and stuff to find out what kind of instruction it is. But a simple way here is I just take the instruction object that I get from the API, and I just check if it starts with the word call. There are no other functions called in this this code, so I know if it starts with the call, it's going to be mprotect, and then all I do is I say take the instruction and skip to the next instruction that's being emulated. So skip over this call and just carry on emulating over this call. So let's just define these functions now. So get instruction at and skip to next instruction. And again, I like to do this because I can just reuse these in other scripts without having to remember which API calls are made to get them. Okay, so let's define this function. So get instruction at, we pass it an address, and the way we do that is we get, so in the API, listings are to do with code and accessing, you know, the listings of code and instructions and things. So we just say current program get listings or get listing, and then we say, given the address that we've got in our emulation, so an address pointing to memory, get the instruction object at that address so that we can find out more about that instruction. So that's all we're doing up here. So if I go back up here, so we're going to get that, and the next thing we're going to do is we're going to say skip past this instruction. So I'll just define that function too. So here we go. There's probably a different way to do this. I think there's on an instruction you can get the next instruction. I think there's a get fall through or something function. You can just, the more you look at the API docs, the more you look at the scripts, you'll find that maybe something you did in a more complicated way, you might find an easier way to do it. But generally the API is quite low level, so you can access all kinds of information and you can use those in any way that you like to build your script. So just do whatever works for you. So this is how I did it here. So I want to skip the instruction. So I get the address of the emulator, so get execution address, and then I get the instruction at that address. So the current address that we're executing, I want to know what instruction it is, and then when I've got that instruction, the instruction object, so there's actually an instruction object if we look in the API. And in there, we can call get next on that instruction, and it will get the next instruction after this instruction. And remember that on a lot of CPU architectures, x86 especially, the instructions vary in the number of bytes, how long they are. You can't just say each instruction is 4 bytes long, so to skip to the next one, you go add 4 bytes to the address. You have to know which instruction you're talking about, which is why the API just, you know, allows us to do this. So we can just say instruction.getNext, and it will give me the next instruction. And then all I do is I set the execution address of the emulator, which I used at the start to set it to the function, to the next instruction after the one that we're currently on. So it means that we're not going to emulate that function. We're going to skip over it, basically. So that's how we do it. There's probably another way to do it, but anyway, that's how I did it. So now what we do, so we if we're on a call, we skip over it, so we ignore that call, because we can't emulate mprotect. And just so you know what's going on, I'm going to print out some more stuff. So I'm going to print out the current instruction that we're emulating. Now finally, we want to, when we've checked everything about the current instruction, we want to tell the emulator to step to do another instruction. We pass in this monitor thing. Again, just so that whatever process that involves, if that's, because some of these are blocking, so it just allows the user to cancel whatever you're doing in your script easily. So that's why the monitor is passed in there. But we just say step the step, and if there's an error for some reason, we'll get that it will return a false, and we know that we can just report an error in the emulation, so we can log that there. So this is our emulation loop. And finally, after we've finished our loop, so we've broken out of a loop, and that could be because it failed in some way, or something it didn't quite get to the end or something like that. So we're just going to check here that if for some reason emulation succeeded never happened, we never got to that condition for whatever reason, so we never returned from that function, and somehow we managed to get out of the loop without locking up the whole process, then we raise an error and say it didn't work. Otherwise, we know that the emulation completed. We returned from the function and we emulated it. So let's just try running this now. See if we've got any errors. Haha. So we ran it. Let's just make this bigger. In fact, I can bring it up to here now. That'll be better. So let's have a look. Yeah, okay, so these are all my logs. So it ran the function to the end, and you can see these values changing as it's going through the algorithm. It didn't. We skipped over the mprotect thing, so that didn't cause any problems. So this should have decoded that memory, which is good. Now, just to clarify one thing is that the emulator has its own memory, so its own copy of memory. So it reads memory from the memory of the process, but when we write memory back to it, or the emulator causes memory to be written back to it, it's updating the emulated memory, which is why we need to dispose it when we finish with it, so we free up any state that's stored by the emulator. So what we need to do now is one final piece here to get this working for our CrackMe, is to make sure that when we've run the emulation, we then take the emulated memory that was modified by when we emulated that function and write that memory to our program that we're currently debugging. Not to the binary, not back to the binary, although you could do that another way. You can do that afterwards if you want to dump it after it's been decrypted. I won't do that now, but to the actual memory that we're debugging, to update the memory that we can see in our debugger so that we can statically reverse it. So that's what we're going to do now. So I'm just going to add another step after here now. So after we've run the emulator and it's not failed, so we did okay, I'm going to add this thing, if update memory, then call update memory. The reason I'm going to add this as a config flag is so that we can easily, it just means it's easy to debug stuff without actually committing any changes. Although in Ghidra, everything you do whenever you run a script that modifies anything, you can always undo. The way Ghidra works is that there's like an internal database that tracks changes to memory and stuff like that, and whenever you do an operation to it, you can always undo it. It tracks the history. So, but it's just useful to do this kind of thing. So I'm going to say update memory. Let's set it to true because we want it to actually update memory after we've done that, and now we can define this function. Okay, so let's add that function. We'll put it down here, maybe here. So update memory. So applying the decoded memory, the emulated memory to our memory, and we're going to do it like this. So we need to get the first address of the decoded memory, which is, remember we set these values right at the start based on our code. So the address that the memory decode is starting from, and the end address. Okay, so we're going to copy all of that from our emulated memory space into our reversing memory space. So that's good. And we're using as address there to make these into address objects. Okay, so because we're accessing the actual Ghidra's the reversing memory that we can see in our, so when we look in here, and when we look on, where do we call it? What do we call it? So it was a label, and we called it input password buffer and that thing. So when we click on that thing, so this memory here is in the Ghidra's kind of reversing memory space. So we want to get, this is what we're going to be updating with our decoded memory. So we're going to get that using current program.getMemory, gives us access to that memory so we can update the bytes in it. Okay, so we're going to have a loop that we're starting now. So we're going to just record the number of bytes we've written, just because it's useful to know that. We're going to take the start address, we're going to start there, and we're going to loop round until we get to the end address, and we're going to read data from the emulated memory and write it to our current program's memory that we're analyzing. So first what we do is we get the emulator, self.emulator, and we read a byte of memory from the address that we started at. Yeah, from here. And I'm just going to print that out. In fact, let's just try and run that now. Let's see if that's going to work. So if I go back to the console, and remember I mapped it to control R, so if I run it, so it's running memory decoder and it's printing that stuff out. So there's lots of zeros in there. It's still running. Yeah, that was funny because it kind of locked up stuff because I ended up, I wasn't advancing byte on here. So so it just got stuck in that loop. It never got to the end, which is fine because we can cancel it. But so we read the byte. So we read the byte and then we want to write it to our current program memory to update the bytes. So memory.setByte, let's just put that there, address, so the current address, and it's the decoded byte that we just read from the emulated memory that we let the function decode. And then we say num bytes written +1 just so that we can record those. And then the important part, so that it all gets stuck in this loop, is address equals address to add 1. So increment the address by 1 byte. So we move to the next byte of emulated memory and write that all until we reach the end address. And then when we finish, we can do this. So we'll just say we wrote that number of bytes. Right, let's try this now. So let's just check. So what we've got is we set up the emulator, we run the emulator. When it's finished, if we want to, if we set this flag to true, we then take the emulated memory and write it to the memory in Ghidra that we're using to analyze stuff with. So let's try running it. Aha. So it ran it, which is good, but then we see this error, Ghidra.program model memory address exception, memory change conflicts of instruction at this. Right, so if all I'm going to do now is undo this, if I look at the memory, where is it? So that label here, if I look at that in my listing, it's all these bytes have changed to 0 now, which is good. But then when it got to the function, so it did all that, and then it got to the function, and it didn't do anything to this. It just threw an error, and that's because I'm going to undo this. If I just, like I said before, when you run a script, edit, undo, or Control Z, and you can see here now it's put that stuff back, which is good. But what I need to do, because Ghidra, when I go changing memory in my script, Ghidra has locked this. Because it's kind of recognized it's being used as a function and it's locked it, so I can't just change it. So I need to just click on here and I need to say clear code bytes. Okay, has that done it? Okay, so clear code bytes, and then when I run this again, let's try, see if it works this time. It runs it, and it says written bytes of decoded memory to that address. Now if I go back to there, yes, it looks like it's changed it. So now if I right click on here, so this is the encrypted function, and then disassemble it, and you can see there's code there now. So we've decoded that area of memory and it's turned it into a function, so that's really good. In fact, if I go to the decompiler view now, this looks more like it. So we've got a call to this function, and it's checking. These are the addresses where the password got copied to. So when it read the password, it read it to that global address space, which was before the function that got decoded. So it's checking it looks like it's checking the password now. It's saying if this value equals M, if that one is space, if this one is double quotes, if this one is not a /, and then it passes an address into this, and it calls that as a function, and if these match, and it calls this one if they don't match. So this looks like the success condition. Let's yeah, so let's if we follow this actually. Oh no, we can't follow it. If we go back, if we look at where this function was called, which was in our main function, we can just click on that address, go to decompile view. So look, this is the function that we just decrypted. So now I'm going to change that to verify. And we can see from this function that we've just decrypted, it takes these two addresses in, and you can see that it's using these addresses to call them as functions. So they're actually functions. So if we go back and we click on these, because we now know that they're called as functions, we see here, we should be able to, and these are in the text area, so we should now be able to disassemble. There we go. Wrong password. So it says there's code here, and when we, if you look in the decompiled view, yeah, it's basically printing out wrong password if we go that way. So these are the success and fail branches. But because they were passed in as addresses into a function that was encrypted, then Ghidra had no way of knowing that they were being called as functions because it wasn't able to analyze that encrypted function. So it just pointed to them as addresses. But we can see now that they're actually functions. And the other one I think is it this one? Disassemble. Yeah, you found the password. So this is what we want to hit. So we know now that if we just set these labels, so we'll call this one wrong. Wrong. We'll call this one correct. And now when we go back to our main function, which references these, if we go back to the decompile view, we can see that this verify function, the first argument that gets passed is the wrong path, and the second one is the correct path, which is what we thought when we looked at the code, because there's all these conditions checking characters in the input, and then it goes to this, which is actually this parameter is passed the fail. Sorry, this is that's the second one. So this is past the success. So this is success. So call this one success or correct. So call the other one correct. So we'll call it correct. And we'll call this one failed. So now all we need to do is see how this works. So if we look at the listing, the assembly code here, we can see that it's storing the address. Remember that the input password gets copied to here, which is also the memory that was decrypted, but it gets used for storing the password as well. So the password gets copied to the start of that. If we click on it, we can see it. Here's a cross-reference. So remember here, the destination for this M copy that we decided was an M copy is this start address that also gets decrypted at the start of the thing, but it's using it as a buffer for the password before the bit that has the function in it, the verifier function, and it copies the password into there. So so if we go back to here now and we look at the verify function, so the way it's using that, it's copying this password buffer into this R8 register, and then it's doing these comparisons, and it's saying it's using offsets in the, so it's copied it to the data section, and it's referencing these by their data ID, and it's sometimes it's easier if I just move this person in the corner. It's easier to sometimes, when you look at this, it's got it's been annotated by the analyzer and stuff, which is good, but it's referencing it as a data in a data symbol. And sometimes it's easier just to look at down in this corner, you can see the raw assembly without any of this annotation that's been added. And I can see here that it said the address of the password, so the fourth byte, so it's checking so not 0, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So it's the fifth character. It's checking if the fifth character is equal to an M. So let's just note that down. So we think that, so password, or let's just call it P5, we think it's checking if it's an M. Okay, let's just save that. Okay, and then it's doing a comparison. Again, if we look down here, it's a bit easier. It's saying the password that was the read from the user, it's saying the 9th byte. So that would be like 0, 1, 2, 3, 4. It's going to be the 10th byte, so the 10th character at index 9. And it's checking if that is a space. Okay. So P10, I'll just put it like that, is a space. Okay. And then what's it doing? It's saying the next character, which is actually, if we look on here, down here, the 5th character now. So you see that the offset number 5, so the 5th index from the password that was read in from the user, it's checking if it's that 22, which is double quotes. If you hover over there, you can see there, double quotes. So it's saying the 5th character, the 6th character, because it's address 5. So P6 equals double quotes. Okay, and the next one is checking the 8, so it's going to be, in fact, let me just make this a bit easier, so that shouldn't, we can call that index 9. We'll get the indexing right. I'll double check this in a minute. So that one that we just checked was if we look down here in the corner, so the 8th, index 8 should be that thing, but actually this is the next one is a jump 0, not a jump not 0, so this is reversed. The decompiler shows us this. If we look at it, it's actually saying that this character, the 8th character, is not equal to a /. So that's important. That would be easy to miss. So it's so the P8 is not equal to a /. That means it could be anything but a /. Good. And is that all the conditions? It looks like that's all the conditions. There are these other comparisons down here, checking if the start is this thing. So it's checking double words, so 4 bytes. It's checking a 4-byte value there with that. We don't see these in the decompiler, which is nice because the decompiler has recognized, if we look closely, that although these comparisons are made, so it looks like it was maybe written in assembly by the developer, probably this part of the code. But you see here, it does these comparisons of other characters, but it never actually does it doesn't do a jump based on those. It's only, although it's comparing them, it's not got any jump following those. It just then does a jump to this RSI is one of the variables here, which is the correct, so it jumps to the correct thing. So all we need then, if we look at this, which the decompiler's got quite nice here, so it's saying the 4th, index 4 is M, index 9 is space. Have we got that? 4 is M, 9 is space. This one, which is, if we look down here, 5th is quotes. Yeah. And the 8th is not a /. So this means that our password is actually not checking every character. So what we should be able to do then is say character 0, let's just put an X for anything that we don't care. So X is 0, 0 is X, 1 is X, 2 is X, 3 is X, 4 is M, 5 is quote, 6 we don't care, so we put an X, 7 we don't care, so we put an X, 8 is not a /, so we'll put an X because it's not a /, and 9 is a space. So remember that space on the end. So let's try this in the CrackMe and see if it works. And if not, we'll just check our code again. So copy that. And we're going to run our CrackMe. paste in the password. Yes, we got it. So that was a hard CrackMe. It was hard for two reasons, I think, because um, one, it was obfuscated, which is obviously we had to either we could have written the algorithm. Let's go back to the main function. So here, so back to the decompiler. So either, where's it gone? Functions. It was init2, which did the decryption. So either we could have written this in Python and just reconstructed this in Python. It's not too complex, so it wouldn't have taken too long to do that. In fact, it probably would have been the quickest way, to be honest. But maybe not. I don't know. We could have debugged it, which would have been fairly easy to do using any debugging techniques. You just put a breakpoint on and debug it. But it's nice to be able to use the emulator. It's good to know how to use the emulator, not just because this could have been complex. It could have been a dangerous file that we didn't really want to execute until we had a better understanding of what it did. Or it might have been the case that it was a piece of firmware that was from some device that we couldn't readily just run in a debugging environment. We just had to do static analysis of the code. So using the emulator is really helpful for stuff like that. So we wrote the emulated code, which looks like this is what we wrote. You can go over this. I'll save this. I'll attach it to the video. So we did that, and once we decoded the memory, we were able then to, where's it gone? Get my label. If I go back to main, go back to decompile. So when we decoded memory, that was this function that was being called. It was obfuscated. Once we'd done that, we were able to in Ghidra tell it to now to decompile that function that had been decrypted. So then it decompiled it, and we saw the checks in here for the characters, which was nice. And once we had the code here, we could look at it in here. It's actually, when it came down to it, this actual code is not too hard, although it's got a few little things to catch you out, like these not equals, and also the fact that it doesn't check every character, but also these comparisons here. If you're just looking at the assembly, you might think you need to set those characters too, but they don't get checked. Maybe that was by mistake. Maybe they intended to, but they forgot to. If they were writing it assembly, they forgot to do the check on the end, or maybe it was just further noise to kind of distract you. But anyway, there we go. So that's quite nice. I hope that was useful, and let me know if you found that interesting, and if you're interested in any more stuff. I'm going to try and put some more videos on to do with different, probably I'll do some more CrackMes and things like that, and maybe look at specific things. But yeah, thank you very much. I hope that was useful.